The Pokemon video games have been around for almost 30 years, and ever since then, players have been catching and collecting all sorts of different Pokemon. But if you're lucky, you can find rare versions of each Pokemon with a different color scheme, called shiny Pokemon. Currently, every Pokemon has a 1 in 4096 chance to be shiny, making them quite rare. Because of this, they have been widely sought after, with some people choosing to embark on shiny hunts. Shiny hunts can often take dozens of hours of resetting, searching, and battling before the shinies are found.
I'm hoping this doesn't turn into another Gurt. Yeah, we reset 13,000 times and
But what if I told you that we can use math to search for shiny Pokemon? By understanding how Pokemon are generated, we can use linear algebra to predict when shiny Pokemon will spawn. Using just information available to the player, we can deduce the data that is being used by the game behind the scenes. For this math exploration, I'm going to be using the game Pokemon Legends Arceus. This game contains some specific mechanics that will enable this method. While you don't need to know all the specifics about the game, the important thing to know is that the player can influence how Pokemon spawn in Pokemon Outbreaks. This is what will allow us to search for shiny Pokemon. First, let's talk about how random numbers work in a computer. How does the game determine if a Pokemon is shiny or not? I mentioned that each Pokemon has a 1 in 4096 chance to become shiny. This chance is decided when the Pokemon is created by the game using the game's random number generator, or RNG. Each Pokemon has several attributes that are randomly generated by the game: shininess, stats, gender, nature, ability, height, and weight. The game assigns a random number to each of these categories. But computers can't just think of a random number like a human can. If I ask a computer to give me a random number between 1 and 12, it can't just roll a pair of dice. Computers need a number as a starting point to generate random numbers. We will call the starting number the seed of the random number generator. So the starting number for generating Pokemon is what we call the Pokemon seed. This number is what we feed into the RNG to create the attributes that you see on the right. Now you might be wondering how a computer turns the seed into a series of numbers. This is the core of randomness in computers. The RNG algorithm is simply a transformation of a number into another seemingly random number. We will go into how this works in a second, but for now I'm going to represent it as a black box. We can take our seed and pass it into the black box to transform it into another number. We will take this new number and use it to determine if the Pokemon is shiny or not. Now, we can apply this transformation a second time, this time on the output from the first step. This will now output a second number, which we will use to determine the HP stat of the Pokemon. This process continues until we have generated all of the attributes that we need. Let's now unpack how the black box works. The ultimate goal of the RNG algorithm is to take a number and transform it into a new, seemingly random number. As with many things in computer science, there are many different possible ways to do this, each with their benefits and drawbacks. Let's use an example algorithm to illustrate one way we could do this. This example uses a very simple multiply-add algorithm. While this algorithm is too simple for real-world purposes, it will be sufficient to demonstrate how a computer can transform an RNG seed. For the sake of the example, we will be working with two-digit numbers. I'm going to start with the seed, in this case 57. I need to take this number and mix it up so I can produce a new number. What I'm going to do is take both digits of the number and sum them up. Here we get 5 plus 7, which gives us 12. Now let's multiply our original number, 57, by the sum 12. This produces a much larger number, 684. I will then add 1 to this result. Since we are only working with two-digit numbers, our output should be a two-digit number. The simple solution to this is just to chop off the third digit. This leaves us with 85, which is the final result of this transformation. You can see from this example that we took 57 and mixed it up to produce 85, which seems random, but indeed has a very predictable and repeatable set of steps to make that happen. If I wanted a second number from this random number generator, I would simply start it over again, this time with 85 as the input. While this is a simplification, this is close to how the actual algorithms for random number generation work. Each algorithm has a different set of operations, with some of them getting quite complex, namely the ones used in cryptography. But this gives you an idea of how a Pokemon's attributes could be produced from a particular Pokemon seed. And because each of these RNG steps are always the same, this means that any given Pokemon seed will always produce the exact same numbers in the same order, resulting in the exact same Pokemon. This will be key to understanding how we can search for shinies. If we can find a Pokemon seed that leads to shiny Pokemon, then we can try to manipulate the game to create that Pokemon. So how are we able to influence the game to cause shiny Pokemon to spawn? For this, we will be using the Outbreak mechanic in Pokemon Legends Arceus. An outbreak is an event in the game where several Pokemon of the same species spawn in the same area in a short period of time. Sometimes, outbreaks will contain a second wave of Pokemon after the first wave is gone. The player is able to influence which Pokemon spawn in the second wave using different combinations of catching and battling the Pokemon in the first wave. This is because the player's actions can change how the RNG advances, which causes it to generate different Pokemon seeds. Thankfully, people have figured out exactly how the game computes Pokemon in an outbreak. And because of this, we can predict which Pokemon will be in the second wave. This uses the same random number generation I described earlier. The key to an outbreak is finding the outbreak seed. This is the starting value that the game assigns to an outbreak when it is created. The game uses the outbreak seed to feed into the random number generator and create unique Pokemon seeds that will in turn generate the Pokemon that spawn in-game. While we cannot influence the starting seed, we can figure out what it is. Once we know the outbreak seed, we can predict exactly which Pokemon will spawn from a given series of player actions, and conversely, which sequence of actions will lead to a shiny Pokemon. So the question becomes, how do we find the outbreak seed? The conventional method to find the outbreak seed has been to hack the Nintendo Switch. Obviously, the game has to store the outbreak seed somewhere, so if you know where to look and hack the console to read its internal data, you could find the seed. Alternatively, if you don't have a hacked Switch, you can initiate a trade with someone who does, and their hacked Switch can deduce the outbreak seed for you. While this does work, I feel like it's not legitimate and takes the fun out of using this method. I want to find a way to deduce the outbreak seed using only information available to the user with a legitimate Switch. So what information is available to us? Well, each outbreak spawns its first 4 Pokemon before the player arrives. This means the first 4 Pokemon of each outbreak are effectively set in stone. Of course, these first 4 Pokemon are generated using the starting outbreak seed. I want you to take a second and think about how you might find this outbreak seed given the first 4 Pokemon. So a natural first solution to this problem is to just try random outbreak seeds to see if they end up spawning the same first 4 Pokemon that we see in-game. And this absolutely would work, as there is only so many possible seeds and eventually we would find the right one. However, the space of possible Pokemon seeds is quite large. Because Pokemon uses 64-bit outbreak seeds, there are 2 to the 64th possible different seeds, or about 18.5 quintillion different seeds. Modern computers are very fast, but trying to check that many possible outcomes, even if you had your computer running 24/7, would take longer than your lifetime, your children's lifetimes, and your grandchildren's lifetimes. And since your great-grandkids probably won't care about this anymore, we have to find a better solution. What we have to do is find a smarter way to use the information available to us to deduce information about the outbreak seed and narrow down the search space. We do have quite a bit of information available to us to begin this process. Each of the 4 Pokemon that are generated at the start of the outbreak contain several important pieces of data that we can use. First, like I stated in the previous step, we can use this data to verify that we have the right outbreak seed. If a candidate seed produces the 4 Pokemon that we see in-game, that seed is the correct one. Second, we know that the outbreak seed and the generated Pokemon stats are related. While the data may go through several steps to do so, the Pokemon stats can be represented as some function of the outbreak seed. So what if there was a way to reverse this function? This is where the linear algebra comes in. You might be asking, what does linear algebra have to do with Pokemon or random number generation? While this may seem unintuitive due to the common ways of explaining linear algebra, I think it can be understood if we expand our mental model of what a matrix represents. The common way of describing a matrix is describing them as transformations of vectors. Matrices can rotate and scale points in space in a predefined way. This is a useful way of visualizing matrices and provides a good initial understanding for what a matrix can do, but I think this often leads to a narrow view of what matrices are for. At a fundamental level, matrices represent functions on input data. This input data could be a point in space, but what if we wanted to input some other data? For example, let's imagine I'm a teacher trying to grade a test. There are 5 questions on the test, and each one is either right or wrong. Let's represent this as a sequence of 5 numbers, where a 1 represents getting the question right, and a 0 represents getting the question wrong. Of course, I could just sum up these numbers to get a score for the test, but I want to be able to weight the questions differently. So let's create another sequence of weights for each question of the test. Now, I can multiply the 1 or 0 for each question by its weight, and sum the results of those multiplications to get the final score for the test. What I've done here is a very simple form of matrix multiplication, albeit with very small matrices. I can expand this example now to include all of the tests from a whole semester. Now there are 5 tests, and each of those tests also has 5 questions. I can represent the student's scores as a 5 by 5 matrix and use the same grading matrix as before. When I multiply these together, the resulting matrix represents the scores for every test throughout the semester. In this case, we are using a matrix to perform a function on the input data. The input data is test scores, and the function is to grade those scores. In the same way, we can use matrices to represent transformations of binary data. Lots of modern use cases for these transformations exist, such as encryption, error correction in Wi-Fi, and QR codes, and in our case, random number generation. For these matrices, each value is either a 1 or a 0. And since we're in binary land, matrix multiplication looks a little bit different. Instead of addition, we use the XOR operation. And instead of multiplication, we use the AND operation. These matrices are called GF2 matrices, or matrices within the Galois field of order 2. Thinking about matrices in this way allows us to represent our random number generator using a matrix. All the shifts and bitwise operations that are used to update its state can be captured with a very large binary matrix. So we can multiply our input seed by this matrix to produce the next random number. The key to unlocking this whole problem is that it is possible to invert these matrices. This means we can reverse the function. In this case, we would be able to use the inverted matrix to convert the output data back into the original input seed. In this case, the output data is the attributes of the Pokemon. So which of these should we use to do this? Let's look again at the data that is generated for each Pokemon. Starting with the Pokemon seed, the game generates an encryption constant, a Pokemon ID, 6 individual values for its stats, an ability, a gender, a nature, and a height and a weight. Since the player cannot see the encryption constant or the Pokemon ID in-game, there's no way for us to use those values. But we can figure out the rest of the values to varying degrees of accuracy. Most notably, although we cannot view a Pokemon's IVs in Pokemon Legends Arceus, we can transfer the Pokemon to a different game to find its IVs there. These IVs will provide sufficient data to reverse the Pokemon seed. Each IV is between 0 and 31, so they contain 5 bits of data. We can pick any of the first 4 Pokemon as our target Pokemon. Our ultimate goal here is to find all possible Pokemon seeds that could have created a Pokemon with these exact 6 IVs. The first step is to build a matrix that transforms the Pokemon seed into the 6 IVs of that Pokemon. What we want to do is for every bit in each of the IVs, record which bits in the Pokemon seed influence that final output bit. The result is that the output bit is the XOR of all relevant bits of the Pokemon seed. If we do this for every bit of all 6 IVs, we create a matrix that transforms the Pokemon seed into our 6 IVs. Well, actually, it's not quite that simple, and that's due to one quirk in the specific algorithm that Pokemon uses. The Zoroshiro RNG algorithm uses addition as its final step in the output values. What that means is that when we generate a value, for example, our attack IV, the algorithm sums 2 different sets of 5 bits to get the true output value. While each of these values on their own are completely determined by the Pokemon seed, the addition makes our attack IV irreversible. Let's illustrate with an example. Let's say I'm thinking of 2 numbers between 1 and 10. I tell you that the sum of my 2 numbers is 12. Can you tell me what my 2 numbers are? Well, not quite, but you can give me several options. You know that it could be 2 and 10, 3 and 9, 4 and 8, 5 and 7, or 6 and 6. This is exactly what we must do for the IVs. Since we lose information when we add 2 values, we represent each IV as 10 bits, 5 bits for each addend. Now we can build our matrix correctly. Let's review what we've done so far. We've created a matrix that transforms any given Pokemon seed into 6 IVs in exactly the same way that the game generates the IVs. However, due to the addition issue, this matrix produces 2 values for each IV, 1 for each addend. These 2 values are summed up to get the final IV value. Finally, we can invert this matrix. This lets us do the computation in reverse. Now we can use the IVs of one of the first 4 Pokemon in the Outbreak to find the Pokemon seed that was used to generate it. But because of the addition issue that I demonstrated before, we don't exactly know what 2 values sum up to become each of the 6 known IVs. But we can brute force these. Brute forcing these unknown 30 bits of information is only 1 billion possible options, which is very feasible on modern hardware. This is much better than the 18.5 quintillion possible options that we started with. What this means is that for every set of 6 IVs, there are about 1 billion possible seeds that could have created those IVs. Now this is where the rest of the information about the Pokemon comes in. Even though there may be 1 billion possible combinations, the fraction of those that produce the right ability, gender, nature, height, and weight is quite small. In fact, we can reduce it to a pool of about 5 to 20,000 possible Pokemon seeds. The last step in this process is to find the Outbreak seed. The previous steps have led us to find a couple thousand candidate Pokemon seeds for one of the first 4 Pokemon in the Outbreak. But to truly unlock the Outbreak, we still have to find the Outbreak seed. The process for this is very similar to before. The difference is that we don't know whether this candidate Pokemon was the first, second, third, or fourth Pokemon generated by the game. The best solution here is to brute force this as well. For each possible order in the Outbreak, we run the RNG reversal on each possible Pokemon seed. We can then check each candidate Outbreak seed to verify if that produced all 4 correct initial Pokemon. While this is a lot of computation, modern GPUs are designed to do massively parallel math like this, and we can find the Outbreak seed in a reasonable amount of time. I realize this is a lot of math to take in, so let's walk through an example to sum all of it up and demonstrate how this process works. For this example, I'm going to reverse a Kadabra Outbreak. This will allow me to find a shiny Alakazam in the second wave. The first step is to catch the first 4 Kadabras that spawn in the first wave of the Outbreak. I'll note down some of the information about all 4 of these Pokemon, like some of their stats, their genders, levels, etc. I'm doing this so that when we search for Outbreak seeds, we can use this information about the first 4 Kadabras to check if an Outbreak seed is correct. Now, I'm going to pick one of the Kadabras to do the reversal process itself. It doesn't really matter which one I pick, so I'll pick the first one. Here you can see the information I've collected about this Kadabra so far. Because Pokemon Legends Arceus doesn't give very detailed information to the player, there's still a lot that we don't know about it. Most importantly, we know very little about the Pokemon's IVs, which is information we will need if we want to reverse the Outbreak. For this Kadabra, there are currently 1.2 million possible IV combinations, and if we were to try to reverse all of those combinations, we'd end up with 13.5 billion different Pokemon seeds. What that means is that 13.5 billion different Pokemon seeds could generate a Pokemon that matches the stats shown here. It is infeasible to search that many seeds, so I have to reduce that number by collecting more data about this Kadabra. To do this, I'm going to transfer it to Pokemon Sword to determine its IVs and ability. In Pokemon Sword, we can see that Kadabra has the ability Synchronize. I can use an IV calculator to figure out all 6 of Kadabra's IVs, which are shown here. With this added information, we've narrowed it down to about 5,000 different Pokemon seeds that could have generated this Kadabra. To actually find those 5,000 seeds, I'll use the IV reversal matrix. As discussed, we have to try 1 billion possible combinations of IV add-ins because we don't know the 2 numbers that add up to each of the IVs seen here. So for each of the 1 billion combinations, we use the inverse IV matrix to compute a candidate Pokemon seed. We can then verify that Pokemon seed by checking the ability, nature, gender, height, and weight. For example, here's a Pokemon seed that produces the right IVs, but does not match the other criteria that we know to be true about our Kadabra. What we end up with is a list of 5,000 Pokemon seeds that produce a Kadabra identical to the one from our Outbreak. The next step is to reverse the Outbreak seed. Like I stated before, we don't know whether this Kadabra was generated first, second, third, or fourth in the Outbreak. So I'm going to try all of them. For each order, I search through all 5,000 Pokemon seeds. Each of those Pokemon seeds produces an Outbreak seed. That means that for each Pokemon seed, we use another reversal matrix to find a candidate Outbreak seed. That Outbreak seed will generate that exact Pokemon seed in that exact position, and we have to check the other 3 Pokemon to see if they match the ones from our Outbreak. After searching all of these combinations, we finally find the Outbreak seed that creates all 4 of the Pokemon exactly how we see them in the Outbreak. Now that we know the Outbreak seed for the Kadabra Outbreak, we can search for shinies. Since we know exactly how the game will spawn Pokemon, we can find the actions that will lead to a shiny Alakazam in the second wave. This particular Outbreak seed has 16 potential paths to a shiny Alakazam, so let's pick one. First, I'm going to catch 3 Kadabra, one at a time. Then, I'm going to ghost one of the Kadabras, which means catching it and then running away. Once I return to the Outbreak, I'm going to catch 2 more and then run away again. Now we'll catch the final Kadabra. Once the second wave spawns, I'll catch a single one of the Alakazam, and then I'll battle 3 of them. And there you have it, a shiny Alakazam. I hope this video provided you with an interesting use case for matrices and how they might apply to computer RNG. And while our use case was just for a video game, many people have used methods like this to break weak cryptographic algorithms. There's a lot more to learn about this topic, and lots of things that I didn't cover in this video, so I encourage you to go out and research more. Thank you all for watching.